You mentioned previously 3 meters per second is the operating limit for velocity in a system. Can you elaborate on that?
Yeah, well, maybe I didn't explain myself clearly enough. It's not really an operating limit, it's a recommendation. If you're pumping clean, cold water, then there is no reason to believe that you've got to maintain any solids in suspension. So if you've got solids in suspension, you need higher velocity to keep it in the flow circuit. Clean, cold water, you can go as low as is reasonable. So what does that velocity actually affect? It affects the pipe diameter, because the more flow you put through, the bigger the pipe diameter, which means the lower the friction losses and therefore the lower kilowatt demand. So from a system efficiency point of view, the benchmark of 3 meters a second for discharge velocities is a reasonable one based on experience. The problem is if you have pumps that are operating at 2,900 RPM, the exit velocity from the pump flange is going to be quite a bit higher than that. So you need to slow that down by putting in an eccentric reducer and increasing your pipe diameter. That means that the installation cost is higher, but the operating cost or the power costs are much lower over time. So it's when you pay your money. That's the important thing.
On the screen we have heat exchangers we sell to the market. The maximum recommended velocity going into the connections of the heat exchanger is 7 meters per second. What would be the recommendation for the velocity going into the pump suction?
Okay, well, basically you're talking about a heat transfer machine, and that will have coils inside it, and the recommended velocity through those coils is determined by the manufacturer of that piece of equipment. From a pump perspective, my recommendation is you look for low velocities in pump suction, probably around 1 meter a second, because you're concerned in an HVAC application with NPSHA. And the smaller you have the pipe diameter, the higher the velocity, so the higher the friction losses in the suction pipework. So my recommendation would be if you look for around 1 meter of a second, you're going to have a fairly low flow rate, low friction losses in the suction line, and less of a problem with NPSHA.
Follow-up question, Keith. Would there be an increase in velocity within the pump?
Yes, there would. That's really what the pump is doing. But the velocity increases in different parts of the pump as the liquid passes through. What does the impeller do to the liquid? It imparts centrifugal force, and when you apply force to a liquid, you accelerate it. So in accelerating the liquid, you increase the energy that's in the liquid. When it goes into the diffuser part or the volute part of the pump, it's actually slowed down again. So there isn't a uniform velocity profile through the pump. The question about whether you actually increase the speed of liquid between the suction and the discharge is a question only of flange sizes. So if you've got an equal flange on both suction and discharge, you won't increase the velocity, but you've increased the energy by adding pressure energy and maybe velocity ahead as well.